Okay. Hi everyone. Hope you're all well and warm where you are. It's been pretty cold lately in Potchefstroom, but today isn't too bad. So I hope it's nice and warm where you are as well. For today, this is the third lecture in our series, and the topic is radiometry, meaning the measurement of radio signals. So at the end of this lecture, you should know some principles of noisy radio signals. You should know how they are measured by a radiometer. You should grasp some important properties of radio receivers and know how we can quantify a telescope sensitivity. So this is a block diagram showing a basic telescope, a radio telescope system. You have a radio source emitting some radio emission, which is collected by an antenna on the Earth. If you have a dish that reflects the signal, reflects it and focuses it towards a receiver. From the receiver, the electromagnetic signal undergoes a frequency conversion, which we will talk about later. And from there, it gets processed. Nowadays, this involves digitization of the signal. There's some signal detection machinery or devices, and potentially some post-detection processing as well. That would include if you're doing interferometry, the correlator or beamformer. But before we get to all of that, we have to talk a bit about noise first. So when a telescope intercepts some radio signal from the sky, that signal gets superimposed onto an existing noise signal within the telescope. And if we believe that that signal is not due to some, that noise is not due to some systematic effect, that the noise is the result of independent random processes, then we can assume that the noise is something called Gaussian noise, which is a superposition of independent oscillations with random phase and amplitude. So these are random fluctuations that are uncorrelated. That's very important. And there's a theorem in statistics called the central limit theorem, which states that if we have a bunch of random independent processes, we take the mean for a variable on each, and we plot the distribution of variable of the means of that variable that we get a probability density function like on the right in the form of a Gaussian function, also called a normal distribution or a bell curve. So in the case of a radio telescope, the quantity, the variable that we will be measuring will be a voltage. So the electromagnetic signal intercepted by the telescope gets turned into a voltage that fluctuates. So if there's only Gaussian noise in the system, that voltage will fluctuate randomly between positive and negative, and over an extended period of time, that averages out to zero. So the mean value for the voltage will be equal to zero. And in this equation for the Gaussian distribution on the bottom, we can get rid of that mu average to give us an equation like on the top left here, which is the probability density function that we will get for the voltage measurements V. And we said that the average voltage is zero, but the signal still contains power, and that power is given by the average of the voltage squared, of the amplitude squared. And that's also equal to the square of the standard deviation of that Gaussian function. Next, we can use an important theorem called the Wiener-Khinchin theorem, which states that the autocorrelation function of a random stationary process has a spectral decomposition given by the power spectral density. So that sounds complicated, but it really isn't. So if we look at the autocorrelation function on the right there, this R function of tau, what the autocorrelation means is you take the voltage at some given time t and you multiply it by the same voltage at a different time, at some delayed time tau. And you multiply them together, and then you take the integral over the delay between those two samples. And so you end up with a measurement called the autocorrelation, which is a function of that delay that you use. And so essentially what this is saying is how similar is the signal at a given moment to some other time. Um, and the very useful thing about that autocorrelation function is that it's a Fourier pair with the flux, which we talked about last week. So if you can go from voltages, measure their autocorrelation, and then use that to give you the flux of the signal. So if you have only Gaussian noise in your system, then the autocorrelation for all values of tau not equal to 0 will be equal to 0 because the voltages are uncorrelated. So there's no correlation between voltage from one moment to the next. So it will be a value of 0 everywhere except at tau equals 0, where it will have a value equal to the power of the signal, equal to the voltage square or the standard deviation square. That means that the autocorrelation function for noise will give you a Dirac delta function. It's 0 everywhere, except at one point at tau equals 0, it has a value of v squared. And we know that the Fourier transform of a Dirac delta function, which will give us the flux, a Fourier transform of a Dirac delta is a constant. So all of this is telling us that the flux of Gaussian noise is a constant value. And this is important because it allows us to measure fluxes from objects in the sky as they appear above that constant noise level in the telescope. So this allows us to quantify things in terms of temperatures. So let's say we are receiving a signal with the telescope with some power P. Then that power will be equal to the effective area of the telescope multiplied by the flux from the source. And remember, the flux is given by the amount of energy per unit time crossing a perpendicular to an area. And then we can define the brightness such that the flux is given by the integral of the brightness of the specific brightness over solid angle and frequency. And so then we can say, let's assume that this signal that we are measuring comes from thermal emission. In that case, we know that thermal emission will have a Planck spectrum given by this B as a function of the temperature. Because in the radio regime, the frequency is a small number, we can simplify that down to the Rayleigh-Jeans law, and then we can rearrange that to give us a value for the temperature in terms of the brightness density. So we have gone from measuring a voltage to defining that in terms of a brightness temperature. And even though we know that most radio signals are not from thermal emission, they're from non-thermal processes like synchrotron radiation and masers, we can still use this concept to define a brightness temperature, to say what would the temperature of a black body need to be in order to produce the voltages that we measure with our telescope. So to give you an idea of some values for that, the brightness temperature of Cygnus A is 10 to the power 8 Kelvin. So Cygnus A is the first radio galaxy that was ever discovered by Grote Reber, if you remember back to the previous lecture. And it's still one of the brightest radio sources in the sky, and it has a temperature of 10 to the power 8 Kelvin. But we should know that's not a physical temperature. The radio galaxy isn't physically 100 million kelvins hot, but that is more measurement of the energy density of the electrons and the magnetic fields that generate radio emissions by non-thermal emission mechanisms, in this case, synchrotron radiation. So some more examples of that. We can divide the temperatures or the brightness temperatures of different objects into broad categories. There are cold objects in the range 100 or 0 to 100 Kelvin. These are typically thermal processes, including the cosmic microwave background at 2.7 Kelvin, some thermal emission from interstellar dust and molecular clouds, and atomic hydrogen. That's the H1 line. Up into the warm regime, that's about 5,000 to 15,000 Kelvin. There you start talking about stellar photospheres and winds and planetary nebulae, and also ionized hydrogen, so H2 regions. And then going up above 100,000 Kelvin, you start talking about hot objects, including the sun, which is at about 500,000 Kelvin. But you could also get supernovae, pulsars, gamma ray bursts, active galactic nuclei, and masers. So if I can be so biased, all the cool stuff is happening in the hot regime. But so why do we want to talk in terms of temperatures in the first place? It all comes down to the addition of voltage terms. So we said that the power that we measure from the fluctuating voltage is given by the average of the square amplitude of the voltage, right? But what if we have two distinct sources of voltage? If we have two independent processes, each producing some voltage, in that case, the addition of those two voltages gives you the V1 squared plus the V2 squared plus a cross term. But in this case, the cross term falls out because the voltages are uncorrelated. So the independent processes, if we assume that they're uncorrelated, the cross term disappears, and we are left with the simple addition of the brightness temperatures. So in other words, this temperature framing allows us to decompose the contributions of different sources of emission in terms of their brightness temperatures, which can be added linearly. So we can define an antenna temperature, which is the total temperature that we measure in our telescope, and that will be a linear sum of the temperature of the source that we are observing, plus some terms for the cosmic microwave background, for the Milky Way, the atmosphere, the side lobes, and some thermal losses. And we can model these systemic effects and noise in order to subtract them from the antenna temperature to give us a very accurate value for the source temperature. And then we can work backwards from the source temperature to derive the flux density of the source. So why do we want to think in terms of temperatures? Because we can add them together linearly and they can be subtracted easily. This is why the most basic setup for a radio telescope is called a radiometer, because literally it can be thought of as a radio thermometer. You're taking the temperature of the sky. So this plot at the bottom here is showing different contributions to the noise temperatures from different sources. So at a typical radio frequency of 1 gigahertz, the contribution for the greatest contributor to the noise temperature comes from the Milky Way galaxy, and then as you go up in frequency, the atmosphere starts to play a more important role, and then there are terms for the for additions due to the temperatures of transistors in the system existing at different temperatures. So it's very important to So if we want to maximize the sensitivity of our telescope, we have to reduce the contributions from the systematic effects and the noise down to the lowest possible value. So that's called the system temperature, and we want to minimize that system temperature down to as low as possible. And we can measure those system temperatures very precisely. These are measurements of the system temperature for meerkats at different frequencies, for the L band at the top and the UHF band at the bottom. And you can see at the L band, we're in the range of about 20 Kelvin to 25 Kelvin. So that's very, very cold, right? That's about negative 250 degrees Celsius. In the UHF band, we get a bit hotter. It goes up to 40 Kelvin. And that is because the contribution from the Milky Way increases as we go at low frequencies. But that's still very, very cold, right? So there's a bunch of really complicated and expensive technology that goes into making the receiver of the telescope as cold as possible to minimize that system temperature. So at the top left is a picture of a meerkat L-band receiver, and on the right hand, it's cut open so you can see what's going on inside. And that copper cylinder in there at the center, I believe that contains the cryostat, which is responsible for cooling the receiver system down to very, very low temperatures using cryogenic techniques. So very complicated and expensive technology going into making Meerkat as sensitive of a telescope as it is. So let's talk a bit about receivers. In radio astronomy, there are broadly two types of radio receivers. There are heterodyne receivers and bolometric receivers. Heterodyne receivers are the typical kind of receiver that you also see in your cell phone, or a Wi-Fi receiver, or FM AM radio receiver. And it's based on a technique called heterodyning, which is a technique for shifting a signal from one frequency to another using a transistor or a mixer. And we'll get to that in a bit. But basically, the heterodyne receiver converts the frequency of the signal by mixing it with a reference signal, and then it passes that signal, a digitized signal in modern cases, through a cable where it can be processed by some other devices. This kind of receiver is used prominently at from the millimeter to meter wavelengths. Bolometric receivers, on the other hand, work on a completely different principle. A bolometer is a device that measures radiant heat using electrical resistance. So on the right is a diagram for this. You have some radio signal incident on a material, and the material absorbs those photons and it heats up a little bit. And because the electrical resistance of that material is dependent on the temperature, the photons cause a change in the total power that you measure in the telescope, and that's what you measure to detect radio emission. But importantly, this kind of receiver only records the intensity of light. So you don't record the phases of the electromagnetic signals that you intercept. You're only recording the intensity, meaning that you don't have any spectral information. On the plus side, you can use this kind of receiver over a very wide bandwidth. So over a bandwidth of 60 gigahertz in this case, which gives you a much higher sensitivity. But this kind of receiver is really only used at very small wavelength, sub-millimeter observations for some photometry cases. So for the most part, vast majority of radio telescopes, including Meerkat, use heterodyne receivers. Here are some important properties of receivers. The quantum efficiency of the receiver quantifies the fraction of photons that are converted into the signal. The noise in the signal is defined as the uncertainty of the output signal, and it's a combination of statistical fluctuations and systemic effects. The dynamic range is the maximum variation in the signal that the receiver is sensitive to. The temporal resolution indicates the smallest sampling time that you're able to use to sample the voltage. The spectral response is another word for the frequency range that you're able to observe. And the spectral resolution says how fine are you able to divide that bandwidth into frequency channels. So this on the right is a diagram for how a typical heterodyne receiver works. So the signal comes in from the left-hand side here into a feed horn, which feeds it into something called the OMT. That stands for the orthomode transducer. And that basically takes the signal and it splits it into orthogonal polarizations. So on the bottom is a depiction of what the meerkat OMT looks like. And you can see it's basically a waveguide that splits the polarizations of the signal, each one going into one of these arms of the OMT. And then each polarization goes into its own, off on its own. And this allows us to store and to recover the polarization information and the signal to use for the Stokes parameters, as we talked about last time. So from the orthomode transducer, the signal goes to an LNA, which is a low noise amplifier, which just amplifies the signal. And from there it goes to a mixer, which mixes the signal with the signal from a local oscillator in order to down convert it to a lower frequency that can be more easily sampled and detected. And then from there it goes to the rest of the detection system, which we'll talk about in a bit. So why do you want to down convert the signal? Two important reasons. The first is that signal losses typically go as frequency squared. So if you want to minimize the losses in the signal, you shift it down to as low a frequency as possible. The second reason is that lower frequencies are easier to manipulate. For a variety of reasons, they are easier to amplify, filter, delay, sample, process, and digitize. We'll get to the Nyquist sampling in a bit. So usually there will be several frequency conversions in a typical receiver system, working until one edge of the frequency band is at 0 hertz. So you take the data with the frequency that it naturally has in the electromagnetic signal, and then you shift it down all the way so that the lowest frequency is at 0 hertz. And that is called baseband data. Let's take a quick detour to talk about how you can quantify the performance and specifically the sensitivity of your telescope. So if you are using a dish telescope, which collects signals from some area and focuses them, that means that you can't see all of the sky at once, right? You only see signals from somewhere within the sky that is collected by the dish. And so you can define a beam pattern as the one on the right, which has a main lobe in the center, and then side lobes and back lobes off to the side. But for the most part, the main lobe is the region on the sky that you are able to observe with the telescope. And so if you make an image with the telescope, it's that region of the sky defined by this main lobe of the beam that you will be able to see. And that lobe, the main lobe, has an angular resolution proportional to the wavelength that you're observing divided by the diameter of the dish. So at longer wavelengths, the beam will be larger. At lower wavelengths, at higher frequencies, the beams get smaller. And then if you build a telescope with a bigger diameter, a larger dish, the angular resolution gets finer as well. But this beam, it subtends a solid angle, so you can define the solid angle, which is basically the area of the sky that the beam is covering, and that's given by this angular resolution squared multiplied by pi over 4, and that is approximately equal to the wavelength squared divided by the diameter squared in steradian. And this allows us to define a very important quantity called the gain of the telescope. And that's defined as the solid angle subtended by a sphere. So remember, there are 4 pi steradians in a full sphere divided by the solid angle of the antenna beam. So that's the omega A we just defined. So the gain is 4 pi divided by omega A, which if we use the formula that we derived above, is approximately given by the diameter of the dish square divided by the wavelength square. And that's also proportional to the effective area of the telescope divided by the wavelength squared. So now if we think back to our definition of flux, it's the integral of the brightness over a solid angle. And if we substitute the Rayleigh-Jeans law in there, we can rewrite this as a function of temperature, solid angle, and wavelength. And if we then solve this equation for the gain, we get that the gain is dependent on the wavelength, and that it's proportional to the brightness temperature divided by the flux, measured in Kelvin per Jansky. So, in other words, the gain is a very important scaling factor between the brightness temperature and the flux. It's basically telling us how efficient is the telescope at turning a flux from the source into a brightness temperature measured by the telescope. And this is why the gain can be used to quantify the sensitivity of the telescope. The higher the gain, the more sensitive the telescope. So that's the case for single dish telescopes. For interferometers, where you have multiple dishes, the gain adds linearly with the number of dishes. So you just add the gain together of each individual dish, meaning that if you want to maximize the gain, you can either build one radio dish with a very large diameter, or you can build lots of smaller ones and then add together the gain. And that's also one thing that makes interferometers very sort of forward thinking, because you can keep building new antennas and adding them to the gain to create a more sensitive telescope. So to give you an example of numbers for these things, the meerkat gain at 1.2 gigahertz, remember it's frequency dependent. If you use 64 dishes, is 2.8 Kelvin per Jansky. Remember, the scaling is proportional to the number of antennas. So if you use half of the meerkat dishes, you get half of that gain. If you add another 64 dishes, the gain doubles. But if we use the 64 dishes currently installed, you get a gain of 2.8 Kelvin per Jansky. And physically, that means when a 1 Jansky source enters a meerkat beam, the antenna temperature rises by 2.8 Kelvin, which is still a very small temperature, right? It's important to remember how low of temperatures we're talking about here. This is why the gain is also called, especially in the engineering world, it's called the DPFU, the degree per flux unit. Another way that we can measure the sensitivity of the telescope is using the SEFD, the system equivalent flux density. and that's given by the system temperature divided by the DPFU, or the gain. So to give you some numbers again, the system temperature for Meerkat at 1.2 gigahertz is about, say, 26 Kelvin, meaning that the SEFD is 26 divided by 2.8 Kelvin per Jansky, giving about 10 Jansky. And you can think of this number as the total system noise power of the telescope. So in general, if you want to maximize the sensitivity of the telescope, the bigger the DPFU, the bigger the gain, the more sensitive the telescope. For the SCFD, the lower the SCFD, the more sensitive the telescope. And this SCFD scale is important because it's an absolute scale that we can use to compare single dish and interferometer telescopes on an equal footing. So this is a plot showing the measured SEFD in Jansky at different frequencies for a number of big single dish radio telescopes. You have the GBT Green Bank telescope in the US, Effelsberg in Germany, Tianma radio telescope in China, Parkes telescope in Australia, and the Sardinia radio telescope. And remember, we said Meerkat at around 1 gigahertz gives you an SEFD of about 10 Jansky. So you can see that the sensitivity of Meerkat is right up there with the most sensitive single dish telescopes in the world. And the more antennas that we add to Meerkat, the more sensitive it's going to become. So if we have in SKA phase 1, we have about 200 Meerkat or 200 SKA dishes. That number is going to go down to like 3 or 4 Jansky. Right. So after the signal has passed through the receiver, it gets passed to some signal processing devices. And basically that means you have to measure the voltages that are induced by the electromagnetic signal. If you have only noise in the only noise in the system, then the voltage induced will alternate between positive and negative values, about a mean of 0. So if you hook up a DC voltmeter, the reading averaged over any length of time will be 0. So that's not ideal. Instead, we want to incorporate a diode, which is a device which only passes current in one direction, so that we can only measure positive or only negative voltages. And the simplest of these kinds of detectors using a diode is called a square law power detector. And in the old days, that square law power detector would literally just measure the square of the voltage and then use that to drive a pen chart. It would literally move a pen which would draw a line onto a piece of printer paper that was continuously rolling. And so in the old days, this was how you would take your radio astronomical measurements, was using a pen that moved in response to the varying signal voltage. Nowadays, we don't use pens, thankfully. We use digitization of the signal. So the telescope takes a continuous electromagnetic wave and it digitizes it into a discrete voltage sequence. So it measures the discrete voltage values. And this is important because there are a bunch of important effects that come into play when you talk about digitizing a signal. In particular, you have to take into account the Nyquist sampling frequency. So to explain that a little bit, let's say that we have a signal in the telescope of the voltages are varying according to a sine wave like this one. Um, and now we have to sample that signal using a particular rate of sampling. If we only sample that signal once every cycle of the signal, so let's say once every peak of that signal, then and then if you're trying to reconstruct the signal, you get a flat line. So in other words, if you only sample the signal once per cycle, you don't have enough information to accurately reconstruct the form of that signal. If we use 2 samples per cycle, we get a sawtooth signal like this one. And so the general principle is if we want to accurately reconstruct the signal, we have to sample the signal at least twice every cycle. And if you don't do that, if you sample it less often, you get an effect called aliasing, which just basically means inaccurate or ambiguous reconstruction of the original signal. And so the Nyquist theorem states that that the sampling frequency has to be greater than twice the highest frequency contained in the signal. So remember, our signal from an astrophysical object it will be the superposition of many independent frequencies. And in order to avoid aliasing altogether, we have to sample at twice the frequency of the highest frequencies in the signal. So to give you some idea of numbers, in the Meerkat L band that observes from 856 to 1712 megahertz, and we downshift that using the local oscillator down to 0 to 856 megahertz. And then the maximum or the minimum sample frequency that we then have to use is twice that. So that's 1.71 gigahertz. And if we invert that, the maximum sample time that we can use, the maximum distance between our samples is going to be about 0.6 nanoseconds. So we have to read the voltage at least once every 0.6 nanoseconds, which is extremely rapidly, right? So let's do some more sums. If we Nyquist sample a band with a maximum frequency nu max over an integration time tau, then we get 2 times nu max, that's the Nyquist frequency, times tau number of samples. So if we have Gaussian noise, the uncertainty delta T on the measurement of the system temperature will reduce with the square number of the number of samples. So the uncertainty on the system temperature is given by the system temperature divided by the square root of the number of samples, 2 nu max tau. So let's insert some figures. If we have a Meerkat integration time of 8 seconds, which if you remember is the minimum dump time of Meerkat, and a maximum frequency of 856 megahertz, and a system temperature at 1.2 gigahertz at 26 Kelvin, that gives you an uncertainty on the system temperature of about 0.2 millikelvin. So remember, a 1 millijansky source, because the gain is 2.8 Kelvin, a 1 millijansky source in the antenna heats it up by 2.8 millikelvin. And so 1 millijansky source will have a signal to noise ratio given by that 2.8 millikelvin divided by the 0.2 millikelvin, which gives you a signal to noise ratio of 14. So even though the source has a much lower brightness temperature at only 2.8 millikelvin than the system, which is a system temperature of 26 Kelvin, we are still able to detect that signal because it stands out above the noise in the system, which is only about, sorry, that should be 0.2 millikelvin. So that's it from me. Let's summarize what we've learned today. So a radio telescope takes an electromagnetic signal and it turns it into a fluctuating voltage. If we take the square of the voltage amplitude, that gives us the power of the signal, which we can then relate to a brightness temperature. The antenna temperature that we measure, which is the total temperature of the system, is the sum of the source brightness temperature and the noise and systemic effects. So in order to detect an object, you have to have a brightness temperature that's greater than the noise temperature. A heterodyne receiver splits the signal into polarization channels, amplifies it, and then shifts it down to a lower frequency. The gain, or DPFU and SCFD, are useful ways to measure the sensitivity of a radio telescope. And then finally, a very important thing to remember, a digitized signal has to be sampled at least twice the highest frequency. And that's it for today. If we have any questions, you are welcome to ask them now. Yes, Kevin, your hand is up.
Yeah, Tiaan, can we just go back a little bit about what exactly the telescope is measuring, what it's actually detecting? So,
Yes.
I mean, I get there's an electromagnetic field that hits the antenna, and it's converted into an oscillating voltage.
Yes.
And we can talk about it in terms of temperature, but we're actually measuring the voltage, right?
Yes.
And that's not it's not the voltage squared or the power or a temperature. It's actually the voltage.
Yes, it's
Right.
a voltage that we're measuring, but because it's alternating positive and negative, we have to take the power of the voltage, which is the amplitude squared.
And so, and I mean, this must be sort of almost at the limit of our electronics to be able to record something every 0.6 nanoseconds, right? I mean, if you were doing this with the light, you wouldn't stand a chance. You'd have to
Yes.
measure something else, right?
Yes. Yeah, I mean
And
that's sorry, go ahead.
yeah, I was going to say, and so, and that also, this assumes that what we're measuring, it's monochromatic light. Or so how would we deal with a bandwidth of light? I mean, how would that? What would you actually be measuring there if you've got, if you want to detect light within a bandwidth range?
Yeah, so for polychromatic lights, which is going to be the case for the vast majority of radio emission that you observe, that just means that the voltage that you are going to measure, which is fluctuating, is going to be the superposition of all the signals uh, at different frequencies. And then when you do the signal processing, you can decompose that signal, you can channelize it. So you can divide the signal up into distinct frequency channels using a Fourier transform. And then each of those channels independently corresponds to the flux within a specific frequency range. Does that answer your
Yeah.
question?
So it's not as if it's not like you sort of tune the receiver. You actually want a width of signal.
Yes. Yeah, you measure a signal which is a superposition of a whole bunch of frequencies, but you limit it within a specific range using a band pass filter. So you say, I'm looking only at signals within this frequency range, and then using a Fourier transform, you then convert, you decompose it into the individual frequency channels.
Okay, thanks.
Yeah, no problem. Paul, your hand is up as well.
It's almost like a follow-on question to what Kevin asked and what you were describing now. But that whole process, because you effectively, discussion you had with Kevin is you left with these voltage, no, you just fit voltages. So you're coming out of this sieve in electronics, you've got a voltage and it's fluctuating over time. And then you
Yes.
convert it to frequencies and you pick up the distinct frequencies because you turn it into channels and each channel's got a slightly different frequency.
Yes.
You want to go through, how does that process work? You spoke about it now in terms of band pass filter. So converting, no, effectively using either a Fourier transform, but converting from that the fluctuating voltage into actual signals per frequency. How does that happen? Is that done electronically? Is it done digitally?
Yeah,
It's quite a process to get out there. You're getting out from just a single signal, you're getting out signals at a whole range of different channels.
Yeah. Yeah, no, I mean, so there's a dedicated device called the channelizer, which deals with um, taking that broadband data and dividing it up into the different channels. And I'm not super familiar with how that actually works in practice. I know it has something to do with Fourier transforms, but more than that, I really can't say.
Okay.
Yeah,
But
it's
do you know if it happens electronically? Is it the electronics that does it, or is it actually a digital like a computer processing that calculates it?
so I
think it
I
will happen in
believe
real time.
I believe the channelization happens after the digitalization. Um, so the signal is already digitized and then it goes through channelization after that.
Okay. Okay. Thank you.
Cool. Any other questions? Joseph, your hand is up. Joseph, you can go ahead. Yeah, Joseph, we can't hear you. Yeah, sorry, can't hear you, Joseph. Paul, did you have another question?
Yes, I did. It's that logic. If you don't mind going through that logic again of how, and you went through it in that.
Yeah, it's hello, hello. Can you hear me? Hello.
So, sorry, yeah, Joseph, we can hear you again. Let's just give Paul a chance to finish his question.
Okay, yeah, my question was more just going through the logic again of how you got a certain system temperature, but you can pick up a signal at a much lower, with a much lower temperature than that.
Yes.
Mind just when you get a chance, just going through that logic again of how that comes about.
Yes. Where was it? After this. So the basis there is that you don't have to compare the yes, so you don't have to compare the brightness temperature of the source to the system temperature directly. You only have to compare it to the noise within the system. So your system is at a constant and well modeled temperature, which you are very certain about as a function of frequency. And so in order to detect some signal above that, it doesn't have to exceed the system temperature. It only has to be measurable above the uncertainty in the system temperature. And so the system, that uncertainty scales as the inverse square root of the number of samples that you take. Yeah, so yeah, you only have to stand out above the noise in the system, which is much less than the actual system temperature itself. Does that make sense?
Yeah, that makes sense. So just needed that clarification.
Cool. Joseph, maybe we can hear you now?
Hello. Okay. Can you hear me now?
Yes. Yeah, we can hear you. Yeah, sorry if we
Okay.
can't.
Because that's the false parameters. How do
Yes. Okay. So yeah, so we can't hear you again,
question
but
on the message?
I can read your question on the chat. So
Okay.
you're asking concerning the two polarizations, how do we obtain the 4 Stokes parameters from the 2 polarization channels? That's a good question. I believe the case is that it splits. So if you remember from the Stokes parameters that we had in the first lecture, maybe let's see if I can go back to that lecture. Sorry.
I can help with that if you want.
That would be nice, actually, Paul.
So if you look at that slide that you had, the slide, and we actually show the 2 different polarization signals coming out of the, I don't know what that piece of kit is called.
OMT, yeah.
The OMT. Out of that, so electronically, the system only gives you an X and a Y output. It gives you your 2 orthogonal components, X and Y. And then digitally, you create and I'm not sure of the exact digital process, but you create an XX signal, a YY signal. You some sort of correlation to create the XX signal and the YY signal. And you also create an XY signal and a YX signal. So even though you're coming out of that, you get 2 voltages, you do these sort of cross correlation to get your XX, YY, XY, and YX.
Yeah. So yeah, as I'm showing here, the equation for the plane of the polarization, you only need 2 values, the fluctuation in an X direction and a Y direction, to reconstruct the circular polarization and linear polarization. And then from that, you can define these IQ, U, and V values as a function of those polarization angles. Does that make sense, Joseph?
Yes, it does. Thank you. Thank you very much.
Okay, cool. Any last questions?
And I'll ask one more in connection with the polarization. And
Okay.
if you go to that slide you had where you actually showed, so I can't remember, you gave the name of that
OMT.
the OMT. If you look at that picture of the OMT, you can see it's got orthogonal components, but there are actually 4 effectively outlets to it.
Yeah.
So I'm wondering if your X signal is, the 2 outlets coming out that are opposite each other give you the 1 signal, and the 2 in the orthogonal to that give you, or added together to get your Y signal.
Yeah, I believe that's what's happening.
So I've just never seen it before in what it looks like.
Yeah.
In reality or even a picture. So it's just
Yeah.
interesting. So I presume the X signal comes up from the 2 opposite, and then the 2 orthogonal opposite ones give you your Y signal added together, because you effectively just get your X and Y coming out of this.
Yeah. Yeah, no, when I was at the Meerkat conference earlier this year, we actually saw these in person as well. They were on a table there, and they're actually not that big, like maybe the size of a milk carton. But yeah, they do the splitting.
Yeah, I'm sort of almost fascinated to see how it looks inside. So how you convert from the incoming signal to this, but I suppose that's a whole nother lecture on its own.
Yeah. But yeah, very, very cool anyway. Okay, anything else before we end? I just want to show the rest of the planning for the lectures. So let's see where we are. We're 12 July. So we're going to have a break for the conferences next. And then the next meeting will only be on the 23rd of August. So more than a month away. And then we'll talk about radiation processes. Cool. Any last words before we end this?
Just to say thank you. Much appreciated for your effort.
No problem. Thanks everyone for coming. I'm really enjoying this.
And will you circulate the slides?
Yes, I'll